In this video, we'll focus on data types. Yesterday, we started with two basic data types, integers, or int, and strings. Integers were numeric values, whole numbers, meaning that there were no fractions or decimal points. Strings were like textual data, like hello world, surrounded in double quotes. One of the services that the .NET framework provides is a common type system, meaning that there are base data types that a .NET programming language like C# or Visual Basic or J++ must implement. The reasons why a CTS exists, it requires a little bit more background information. Let's just wait before we discuss that. But each data type has some limits on what it can store, and those limits are based on the size of the bucket. We used that bucket analogy yesterday. The size of the bucket required in the computer's memory. So let's take a simple int, for example. We said it can hold numbers, but let's get a little bit more specific. The int data type occupies 32 bits of memory space, and as a result, it can create a number or hold a number from negative 2,147,483,648 to a positive 2,147,483,647. All right, so mind-boggling, right? What does 32 bits of memory space really mean? Just to map that out, your computer probably has 2 gigs of RAM, maybe 4 gigs. Well, it takes 8 bits to make up a byte, and you have 2 or 4 billion bytes of memory if you have 2 gigs of RAM or 4 gigs of RAM. So comparatively, a single int that you declare is a very, very small value. And you can think of a bit as an on-off switch, just like you have on your wall. So let me show you how all this works. And I apologize if you already know this, just bear with me and I'll get through it as quickly as I can. We said that an int requires 32 bits. Let's trim that down because I can't represent 32 bits in a video. It's too many values. But we can trim that down and only show 4 bits and show kind of how the counting system works. So let's think of just 4 simple on-off switches lined up right next to each other. Each one of those on-off switches represents a value. The first one represents the value of 1. The second represents the value of 2. The third one represents the value of 4. The fourth one represents the value of 8. And it continues on, like 16, 32, 64, 128, 256, 512, and so on. Okay, but let's just work with 4 little switches for the moment. If that switch is off, then that means that the value is 0. You don't add whatever it is that switches value to the count count. Okay, so 0 represents off and 1 represents on. Bits are 0 or 1. They're true or false. Switch on or off, right? So if I wanted to represent the number 1 in the computer's memory, I would represent it like this: 0, 0, 0, 1. Okay, 1, 1, 0, 2s, 0, 4s, and 0, 8s. If I wanted to represent the number 2, I would do something like this: 0, 0, 1, 0. 0 1s, 1, 2, 0 4s, and 0 8s, and so on. The number 3, 0, 0, 1, 1. A 1, a 2, no 4s, no 8s. The number 4, 0, 1, 0, 0. No 8s, 1, 4, no 2s, no 1s, and so on. 5, 6, 7, 8, 9. 9 would be what? 1, 0, 0, 1. I'll take an 8, I'll skip the 4s, I'll skip the 2s, and I'll take the 1. Add them all together, you get 9. And so just expand that to 32 bits, and now that's how you get this massive negative 2 billion to positive 2 billion that can fit in a single byte of the computer's memory. And remember, there's like, what, 2 billion bytes that you have with 2 gigs of RAM, okay? So I just taught you how to read binary. It's as simple as that. That's how computers work, on-off switches. So when we say that there are 2 gigabytes of data, we're really saying that there are 2 billion microscopic on-off switches. By turning them on and off, we have a miniaturized abacus just able to store data. To store an int, we just need 8 switches devoted to that purpose. Now, here's the important thing. The .NET framework reserves those 8 switches on your application's behalf, so no other application can try and use them. It also releases that reservation on those switches once it's through with them. Admittedly, what I'm doing right here is a gross oversimplification, but since you're getting started, it can serve as a working definition, and you can build on that later. Okay, so we said in C# we use the keyword int. If we were writing in Visual Basic, we would use the keyword integer with a capital I. They're both keywords. Behind the scenes, they're using .NET Framework's Common Type System, or CTS, definition of an integer, namely system.int32. That's really what's behind the scenes. So we could just as easily declare a variable just like this, system.int32x equals 3. Now, honestly, that's a little bit discouraged. For readability's sake, you should always use the C# language specific version of any .NET type or .NET construct. Other people might argue with that. You might have a lead developer on a project you're on that feels very strongly that you should use the .NET types, but honestly, I believe it's pretty generally accepted practice to only use the C# types. I think Microsoft even recommends it. Okay, so there are actually other numeric data types besides int. Here's a quick chart. You have sbyte, byte, short, uint, long, ulong, float, double decimal, bool. What? Why do you need all those? Well, honestly, they're for some very specific situations. Many of them are. Of all of those, I think you're going to find yourself warming up to just 3 of them 99% of the time. You're going to need bool, you're going to need decimal, so that you can do some decimal points, you know, to represent money or whatever the case might be. And you're going to need byte, and I'll explain why much later on when we get into SQL Server. Okay, for text data, there's really 2 options. We've already talked about string. It represents a string, a listing of alphanumeric characters, but there's also something called a char, which represents a single Unicode character numerically. We're going to use char, but we're going to use it much later on when we're working with streaming data from a source, say like the internet. For now, I just want to focus on the string data type. It has a .NET Framework class library equivalent called system.string. What's the difference? Again, nothing. It's just capital letter. It belongs to the system, to the .NET framework. We want to use the C# equivalents like we already talked about. The string class is pretty powerful since it has a number of additional methods, just like the console application had. And we'll look at many of those soon because string manipulation is a big deal whenever you're working with data in your applications. All right, there are also data types for special things like dates, but those belong to the .NET Framework class library. There's no C# equivalent or shortcut for it, so to get the current date and time, you would write a line of code like this. Date time right now equals the datetime class dot now, and we're calling the now method because, again, we see the parentheses. And that's how we get the current date and time. But date time is a type, just like string is, just like integer is. It's a more complicated type because it holds a more complicated value that includes year, month, day, hour, minute, second. Okay? And when you start to think about it, just about everything in .NET is a data type. Most of the classes in the .NET Framework class library can be used as a data type. Admittedly, they're much more complex than int and bool and decimal, but they're data types nonetheless. And this thought is going to be more clear as we talk about object-oriented programming in the next couple of days. So stay tuned for that. Okay, so I said all of this to say the following. Remember yesterday when I wrote this code. Let's look at our Visual Studio IDE where we have int x equals 7, string y equals Bob. The first try, remember, we printed out 7 Bob here in the console window, and then we went ahead and we tried to create a second example, and we get the red squiggly line under the x plus y. And I asked, do you care to take any guesses on why that might be? And the reason is because you're attempting to fit a square peg into a round hole. You're trying to put a string, which is a large piece of data, into an int bucket. And the int bucket can't handle it. All right, makes sense. But then why did this work? Well, because the string bucket is a really big bucket. It can hold a lot of information, and tacking on an extra character, small potatoes, not a big deal. But there's more to it than this. In this line of code that I have highlighted here, string my first try equals x plus y, it would have been better had I wrote it this way. X is really an integer. Let's call the toString method on x. And you're like, whoa, what is that? How did you get a method on an integer? Well, the fact of the matter is that all data types have a common ancestor called system.object. And that ancestry means that they have that they take on some common characteristics of their ancestor. They're all objects. They're not just, in other programming languages, they might be inherent types, but in .NET, they're all part of or inherit from system.object. And system.object defines a toString method that means that even our integer gets a toString, which converts the value of x in this particular implementation, which is a 3, which is a character 3, and it turns it from a numeric 3 into a string 3, a character 3. Okay, so there is a different connotation between the two. To you and me, that's not a big deal. We can do that in our head. I live at 4110. Or I could convert that easily to 4,110. Probably took about the same amount of brain space, right? In a computer, it has to work a little bit differently. The computer needs to know which 3 you're talking about because, again, it needs to know how to treat it and what bucket that it fits into. So x.toString worked the same as just x. So why did we have to? Why did this work? When there was really what was required behind the scenes was to add a toString. Well, the C# and the C# compiler are helping you out a bit. It implicitly converted the value for you. Okay, so what if we try to do this? Let's try to let's just comment out some code here, and instead we'll write this. Whoops. So you can see I've already got a little squiggly line underneath my X here. This doesn't work. You're going to have to try one of two things. You can try to cast the value X to an integer since it's currently a string, and you can try to do this right here. However, as you can see, this really didn't work. If I hover my mouse cursor over it, it says cannot convert type string to. The reason why I'm going to have to explain a little bit later. I don't want to take the deep dive into C# at this moment. So this doesn't work. What's our other choice? How can we get this 3 to be set into the value y? And to do that, I'm going to have to use int.parse. And what this will do, it's using the int data type's parse method, taking in a string and converting that, parsing it, the string, into an integer, at which point then we can successfully use that integer y now. So we'll revisit this and talk about the difference between casting and conversion later on. But I think that's pretty much it for this video. I just want to recap. What did we talk about in this video? Quite a few things. First of all, the .NET framework has a common type system allowing all .NET languages to share data between them consistently. Each language can have its own shortcut so that you don't have to use system namespace. But under the hood, all .NET programming languages rely on the system namespace, the .NET framework, the common type system's definition of what those types really are. Okay. Number 2, there are many data types, each created to serve a specific purpose, which is great, but oftentimes a subset of that entire list is all we really need. So we already picked on string and int, and we're going to add byte, bool, and decimal to the data types that we'll be relying on, at least at first in our experience with .NET. Third, we talked about how values are stored in memory, basically explaining how bits translate into numbers and how different data types take up more memory, or rather how they occupy more switches than other data types. Number 4, we talked about how even basic data types have methods that we can access using the dot notation, such as int.parse or int.toString or things of that nature. And then 5th, we talked about data type conversion and casting, and we need to come back to that at a later date. Okay, so that's it for this video. Next up, let's build on what we learned about with the if statement yesterday and add some additional decision statements. We'll see you in the next video. Thank you.